Maybe I got that. Remember how he said?
Okay. 1 second, get this stuff away. All right. So this week's lab is just procedures and functions. I'm hoping that you can finish this lab relatively quick so that you can start on the next lab before next week. It will be posted. But even if it's not posted, I am going to show you how to do the lab on Monday. It is the memory lab. So the memory lab is, like I mentioned, the hardest lab, but it will help you a lot with the final project. And that's not just because the final project is also going to be working with memory, but because they're both high-level state machines. Right? And once you know how to make the high-level state machines and implement the high-level state machines, you can create much more complex systems, right? All right, so your procedures, they're kind of like functions in C code, and the same thing with functions. It's just that procedures can do a little bit more than functions in VHDL. But really what we're trying to do is, if we have these common pieces of code in several different places in our model, then we can kind of compact that, put it into a procedure, and then call the procedure. And that will make our code more readable, more easily understood, because you can give your procedure a good, meaningful name, right? And the procedures can have timing controls, and it can also call other procedures or functions. And this is what a procedure looks like. You have the procedure, keyword, the identifier, which is your name for it, your input-output declarations, so it's like the entity, right? And then you have any variable declarations and your procedure statements, and then you have end. And the procedure can have 0, 1, or more arguments. And the values are passed through it, through the arguments. And your arguments can be input, output, or in-out. So here is an example of a procedure. So it's procedure, right? That's the keyword. And then has procedure is just the name. And then we have one input, din, which is of type input. It's a standard logic vector. That's 8 bits. Dout, type output, standard logic vector, 8 bits. And then here are our variables. We have k, which we're using as our looping variable, and we have count. And then this is the beginning of our procedure. And in our procedure, we have this for loop. And just as a reminder, for loops are not sequential in VHDL. They are basically going to be copy paste the code, but with different numbers. Right, so for k is 0, we're going to assign the output most significant bit to the inputs. Well, not the most significant bit because we're subtracting count. The outputs least significant bits to the inputs most significant bits, right? And then in the next copy paste of this, we are copying and pasting the most significant bit of the inputs into the outputs again, but at a different bit. So once we copy paste this for the 8 bits, our output is just 8 bits of the most significant bit from the input in this case, right? Because we're always DN at 7. So all this procedure does is takes the most significant bits of the input, copies and pastes it to all of the bits of the outputs. Are we good with this procedure? And the key difference, again, is just that procedures can have these timing controls and multiple outputs. Whereas the function, only a single value can be returned from executing the function, and all of these conditions must be true of the function. There's no delay, timing, or event controls. So it's purely combinational. It returns a single value. It has to have at least one input argument. The procedure can have 0 input arguments, right? There's no outputs or in-out arguments because you only have that one defined outputs. And there are no non-blocking assignments. That goes back to it is purely combinational. So functions may implement only combinational behavior. So they're going to compute a value on the basis of the present value of the inputs and return a single value. And each line of code in the function is going to be sequential in that they are not non-blocking. So it's not sequential in the sense of sequential code, but sequential in the sense that if you write it in the data flow logic way, if you assign something and then you use that assigned wire, it will have that assigned value to it. And these are going to be called as functions on the right-hand side of a statement. So here's your example. You have the keyword function, your identifier, inputs, declarations, and then your return type. And then you have variable declarations if you need them. Then your function statements, and then end of the function. And this is how you call the function. So you're going to assign it, the output, to this wire or vector of wires. And it has this assignment operator, which we're very familiar with, right? And then you just call the function and the inputs. And it basically just instantiates this combinational logic block, and the output is connected to it. So this is a lot easier and cleaner to read than if you make a combinational logic block with an entity, and then you instantiate that entity, and you connect it with structural modeling. Right? You could do the same thing. It could be purely combinational, but this is a lot smaller, simpler. And if you're going to call it many different times, it will be easier to read, easier to understand. And the other thing is you can call these functions within process blocks. So if you are doing something like a pipeline implementation that we'll talk about later, it will be useful to have these things. So here is the function. It's implementing something a little different than the procedure was. So we're calling it the same name, has function, and it has an input 7 down to 0. And it's going to return a standard logic vector. And these are our different variables. And we're returning this standard logic vector at the end. Reverse bits. Yeah.
How come in the first function you showed us had an output? This one only has an input.
Because this one, you don't specify outputs. You can only have one output, and it's just whatever you're returning. You just specify the output type, which is standard logic vector. Or are you going to return just standard logic? Or are you returning a variable type that you made, like the states? You make the state type, right? So for this one, we again are doing a for loop, but we're doing it a little bit differently. We are assigning the most significant bits of our return variable to the least significant bits of the inputs. And then on the next iteration, the second most significant bits, second least significant bits. And we keep going until we get to the end of both of them. So the output is just the reverse of the inputs. So that's why it's called reverse bits. So if you wanted to make this function have a more meaningful name, you could call it maybe reverse. Right? And then if you wanted to call the function, it would be funct. Whatever you're assigning it to, it needs to match the expected 8 bits. And the identifier in this case is has function, but maybe, like I said, reverse would be more appropriate. And then you have your input. So you will be making a procedure that adds and a function that adds. And that is the two things that you're going to do for this lab. Yeah. Yeah. A function can only have a single value return. So if you wanted to have kind of those two outputs, you can append them together as one standard logic vector. But then you would have to know in your other code that that one variable that you assigned actually contains those two values. And you have to extract them out. But if you need multiple returns, that's what procedures are for anyways. Because a procedure, you can have multiple outputs. The functions are nice because you know if you're calling a function, it's purely combinational.
Are they on the architecture or are they outside of the architecture?
These would be outside of architecture. Okay, so that is your lab. You're just going to make two adders. One is a procedure, one is a function. And it's really just to show you how to use procedures and functions, how to make them. Yeah. You would call them, like if you're going to use the procedure or use the function, you would call them inside process block. Yes. Yeah. Mm-hmm. Yeah.
Do the inputs and outputs sort of the function, but do they need to be declared in the entity?
No.
Oh.
They're declared as the function. Okay. So I'm going to use the rest of this time to teach you the algorithm that you are going to implement for your final project. Make sure that's the recording saves, because you are going to want to use this most likely. Okay. So the final project, you are going to implement inference for hyperdimensional computing. So hyperdimensional computing is a lightweight machine learning algorithm. So it's similar to neural networks, convolutional neural networks. We've all heard of those, right? But convolutional neural networks and neural networks, they require billions of operations on inference. And as we all might know, they run mostly on servers, right? You send your data from your phone or whatever device you're using to some server where it gets processed, and then the result is sent back to you because it can't run on your phone. But hyperdimensional computing is more lightweight. It would be able to run on your phone. And this is just some examples of machine learning in our daily lives. It's all over the place, right? We have some self-driving cars using machine learning. It's in gaming. We have machine translation. The finance industry uses it. It's all over the place. But as I mentioned, there are a few challenges with current state-of-the-art machine learning. One example of this challenge is Google's AlphaGo. So AlphaGo is just Google's machine learning, AI, whatever you want to call it, that plays the game Go. And AlphaGo was able to beat the top Go player in the world, VHDL. And this was back in 2018. But AlphaGo, it runs on 2,000 CPUs, 300 GPUs, and it took a team of more than 100 scientists in order to create it. And this is like a server farm, right? And in order to run this, it's 1 megawatt of power. So one game of Go played by Google's AlphaGo costs $3,000 in electricity. But if we look at VHDL, his brain operates around 20 watts. All he needed before the Go game was a hamburger or a coffee, right? And if you consider his whole entire body, he's operating at around 100 watts of power. And the other thing, like about a year or a year and a half after AlphaGo beat VHDL, VHDL beat AlphaGo the next year. So he's better at it, and he's much more efficient, right? So what we should do is, we know that the human brain learns much better. We have these different properties. It's low power, like I mentioned, 20 watts for your brain. But traditional computing with machine learning, high power, like a computer is in the kilowatts. The server farm is in the megawatts, right? Our brain is also fault tolerant. Our neurons die as we age, as we hit our heads, but we still remember our core functions and everything. Whereas the machine learning algorithms, they are not very tolerant to noise. Like if you have a machine learning algorithm that is able to recognize the digits like 0 through 9, and then you just give it an upside down 5, it has no idea what that is anymore, right? The human brain is also highly parallel with billions of neurons and trillions of connections, whereas with traditional computing, we have limited parallelism with 4,000 cores for GPUs and hundreds of cores for CPUs. The human brain also learns very quickly. If you show a toddler an apple for the first time, you only need to show him one apple, right? And you ask him 3 seconds later, you bring a new apple. What is this? They'll tell you it's an apple, right? But to train a machine learning algorithm, how many apples do you have to show it? thousands. It needs to see thousands of apples before it figures out what an apple is. And then going back to that, if you introduce a banana to a toddler right after you taught them what an apple was, they can learn what the banana is, and they can recognize the banana, and you bring the apple back, they'll remember what the apple is, right? But if you introduce a new output to the machine learning algorithm of a banana, and you teach it what a banana looks like, suddenly it doesn't know what an apple is anymore. You have to retrain it to learn what an apple is. So because of all these reasons, we're rethinking what it is to compute with machine learning and designing computers based on principles of the brain. So this is where hyperdimensional computing comes in. Hyperdimensional computing is operating based on this sparse distributed memory model of the brain, where you have this dense input from our sensory organs, and it gets mapped into a very high dimensional sparse representation in firing neurons in our brain. And like I mentioned, this is called the sparse distributed memory model. And the different patterns of neurons firing in your brain correspond to different things that you've memorized. So when you see an apple, a distinct pattern of neurons firing in your brain is shown. Whereas if you see a banana, it's a different distinct pattern. So we're going to represent this in computing with these very large vectors called hypervectors. So if we have like the color black, we're going to give it this vector of 1s and -1s. That represents the color black. And we can do the same for the color white. And then we're going to use these hypervectors as our basis for operations. And one of the key factors of these base vectors is that they are pseudo-orthogonal. So that means that their similarity is close to 0. And by similarity for binary inputs like this, we just mean that around half of them are expected to be different. Right? So our operations on these different values, we have bundling. Bundling is memorization. So if we have these different hypervectors, A, B, C, D, and we bundle them A, B, and C into H, this is just element-wise addition. We can then say that the hypervector H has memorized A, B, and C. And if we do this similarity metric between H and A, we'll see that the similarity metric is much higher than 0, where 0 is defined as half of them matching, right? But if we do the similarity metric between H and D, because all of these vectors are orthogonal to each other, we're going to see that D is not found in H, so it has not memorized H. And this similarity metric will depend on your data type. Like after we bundle them, it's no longer binary. We have now integer values stored in this hypervector H. We'll need to use something like dot product or cosine similarity as a similarity metric. But if we keep everything binary, then we can use Hamming distance, which just counts the number of mismatches. And then with this operation, we can do something like this. So we have these different images. We encode them to hyperdimensional vectors, hypervectors that represent each image. And then we can bundle them all into H. And then we can ask questions like, if we have this new input, we encode it, the banana, and we do the similarity with the banana and H. And if we have a very high similarity, we know that we saw a banana. The other operation that we're going to cover is binding. So binding is used to associate different information. And some of the key different properties of binding is that it's orthogonal to the originals. So if you bind A and D and call that H. Then H similarity metric with A is going to be close to 0. H similarity metric with D is close to 0. It's also reversible because our original vectors are just 1s and negative 1s. So if H is A times D and I multiply A again, I just get D back. Or if I multiply D again, I just get A back. And it's because of the identity, right? Because A is going to match A in every single dimension. So if it was 1, 1 times 1 is 1. If it was negative 1 times negative 1 is, again, 1. And with association, we can do something like this. So we have our animal hypervectors from before, and now we're creating a new hypervector that represents the animal category. So we're going to associate all of the animal hypervectors with the animal category and all the fruits with the fruit category. And again, bundle it all up into H. Then we can do something like this. If we multiply H by fruit, then we can extract all of the fruit information from H and see if fruit is in it. Whereas if we get all the fruit information from H and we see if the animals are in it, then we'll get a very low similarity score. So now that we know these operations, yes. In hyperspace. So yes, but no. You don't have to just know that orthogonal means the similarity score is very low. So now that we know how these operations work, what they are, we can encode some feature vector. So let's say that we have this feature vector with n features. It can be, say, a grayscale image, like 10 by 10. We would have 100 pixels. So we would have 100 features, right? And then since it's grayscale, let's say it's 8 bits. So it can have values between 0 and 255. We first need to create these different hypervector banks. So this hypervector bank we call ID hypervectors because they are encoding the positional information. We generate one ID hypervector for every single feature position. So if we have the 10 by 10 image, we have 100 position hypervectors or ID hypervectors. And then this hypervector bank is called our level hypervectors. And these are encoding the value information. And we can create as many level hypervectors as we want. But if we go back to the grayscale example, 8 bits, we have 256 different combinations, 0 through 255. One way to ensure that we don't have any loss in our encoding is we create 256 level hypervectors. One that represents 0, one that represents 1, all the way up until 255. But we could do something like we just want to create 50 level hypervectors. And then 0 through 5 is corresponding to the first level hypervector. And then 6 through 10 is the second level hypervector, and so forth. But then we lose some clarity in our encoding. And these level hypervectors are not all randomly generated. The first one is randomly generated, but the second one is a mutated version of the first one. And that's because they're encoding value information. So we want the level hypervector representing 0 to be very similar to the level hypervector representing 1. And then we take the level hypervector representing 1, mutate it a little more. So 1 and 2 are still very similar, but now 2 and 0 are less similar than 1 and 0. And we do that until the end. And by the time we get to the end, the level hypervector representing 255 should be orthogonal to the hypervector representing 0. And now that we know how these are made, we can encode. So first pixel value, we get the ID hypervector that corresponds to the first pixel value. And we take the value of the first pixel, look up the level hypervector that represents that value, and then we associate that ID hypervector with that value or level hypervector. And this is just element-wise multiplication. Right? Then we do the same thing for the second pixel. The ID hypervector that represents the second position, level hypervector that represents the value of that pixel. Associate and bundle. And we do that for all of the features, or all of the pixels. And just so that we know, so we started with a dense 100-dimensional feature vector image, 10 by 10 pixel image, right? These are 10,000 dimensions. So this operation here, the element-wise multiply, this is a 10,000 dimensional vector. This is a 10,000 dimensional vector. I element-wise multiply them. I get back a 10,000 dimensions times 10,000 dimensions element-wise. What's my result? It's still 10,000 dimensions, right? And that's the same for all of these individual pixels, right? And then I'm element-wise adding that resulting 10,000 dimensional vector with this resulting 10,000 dimensional vector. So again, element-wise add 10,000 dimensions with 10,000 dimensions. I get back 10,000 dimensions, right? Element-wise. The first one is added to the first one, second one is added to the second one. So in the end, H is again a 10,000 dimensional vector. So we're going from this dense 100-dimensional feature vector to this sparse 10,000 dimensional pattern that represents that feature vector. So that's encoding. That's how we get these things into high-dimensional space. Here is training. So say we have a whole bunch of images of cats. Right? So we're first going to encode them using the encoding that we just went over and gets one hypervector per image of each cat. Then we're going to bundle up all of those encoded images into one class hypervector that we're going to call this cat hypervector. So again, this is 10,000 dimensions. And then because we want to be efficient, we're going to also quantize the cat hypervector. If a dimension is negative, we make it -1. If it's 0 or positive, we make it +1. And now we have this binary pattern of -1s and 0s that generalizes a pattern representing cats. We can do the same thing with dogs. Right? Encode them all, bundle them all up. Now we have a class hypervector representing dogs. Right? And then for inference, we get this new picture that we've never seen before. We encode it with the same encoding as before. And we get this query hypervector that is a pattern representing this image of this dog. And now we want to see how can we classify this image. We're going to do this similarity check between the query and the class hypervectors. And we're binary, So our similarity check is just count the number of mismatches. Whichever class hypervector has the least number of mismatches is the one that we're saying is the output. So hopefully in this case, it would be the dog hypervector that has the least number of mismatches, because this is the general dog pattern representing dogs, right? And this is a pattern generated from an image of a dog. So they should be similar. Whereas this query hypervector should be orthogonal to the cat hypervector. And one of the benefits of this was, like I mentioned before, you show a toddler a banana, it doesn't forget an apple, right? With HD computing, if we wanted to add a third class here, say images of birds, we don't forget what a cat is. We don't forget what a dog is. It's not affected by this new class. We just simply encode all of those images of birds with the same encoding, bundle them all up, we get a new class hypervector called the bird hypervector. But for traditional machine learning, you have to retrain all of your weights, right?
It's going to match up what it is.
It just adds more memory. Like we would add a third hypervector. So here is comparing HD computing to deep neural networks on some data sets. So this is the accuracy on the y-axis, and we can see HD is blue, deep neural networks are red. So deep neural networks have a little bit more accuracy, right? It's a little bit taller for all of these data sets, but HD is close, right? And the other thing is, on the x-axis here, we have the number of retraining iterations, and it's log scale. So we have 10 and then 100. The blue line is HD, red line is deep neural network. With HD, after just one pass over the training data, we're fairly accurate. For the deep neural network, starts from random, right? And that goes back to what we talked about before too. If you show a toddler one apple, they remember what an apple is. If you show them one banana, they know what a banana is. With traditional machine learning, you have to show it 1,000 apples, 1,000 bananas. And the other thing is with HD computing, we can reach our convergence accuracy in just a few retraining iterations, whereas the deep neural network needs hundreds. So HD computing, you can use this high dimensional data and apply the learning algorithm to many different applications. We are talking about classification, but it is also being used for clustering, regression, reinforcement learning, recommendation systems. So the key points of this algorithm is that it's lightweight and it's designed from the principles of the sparse distributed memory model so that we can get something closer to the power footprint of a human, right? Rather than, it's almost cartoonish, right? This comparison of 1 megawatt versus 20 watts. So for your final project, and the final project document is available on Canvas, so you can already look at it. You are going to implement inference. So you just have the trained class hypervectors, and you need to load in some encoded query hypervector, and you're using Hamming distance as your similarity metric. You just have to count the number of mismatches. And then whichever one has the most number of mismatches is your output class. That is the basis of your final project. You can achieve more with your final project. There is extra credit available. And there are essentially two different ways that you can achieve extra credit. You can improve on your first correct design. So again, the first part is just get a correct design of inference. So you can improve on it by making its performance better. That would give you extra credit. Or you can also implement a correct design for the other stages of hyperdimensional computing. So you can do encoding. I can show you well, you already know initial training. It's just bundling them all up, right? So element-wise addition. So you can do that. You can do retraining. I did not show you how to do retraining, but if you want to, I can teach you very quickly how to do retraining in hyperdimensional computing. And those are the main. You can implement a different encoding. There are many different encodings for HD computing. And essentially for each additional thing that you want to do for your final project, you can get an additional 20% on the final project grade. But the first thing is get the first correct design. So we have some time. Do you have any questions on the final project? You are going to want to maybe refer back to this lecture a few times to understand the encoding, specifically the inference parts that you're going to implement first, right? But other than that, you guys have your lab today. And next week is the memory lab. And like I mentioned, the memory lab is going to be highly helpful with the final project. So, any questions? To learn before, you should know high-level state machines. So if you haven't studied the high-level state machines yet, and you've only come to the lectures and gone over the lecture stuff, you need to study high-level state machines. Yeah.
We have a poll you code today.
Yes. Your poll code today is 639, I think. Yes, 639. Any other question? You will learn, you will use Python, but you are not going to have to learn it completely. Because one of the key things that you need to do as a digital logic designer is your clients will give you an algorithm. And they want you to implement that algorithm in digital logic, right? But you need to make sure that your algorithm is correct, that you implemented. So you have to print things out from the algorithm that they give you, and then compare it to your waveform that you get from your digital logic implementation. So that's the reason that you're going to use Python a little bit. You're going to extract some of the information from the Python program that I give you, which is the algorithm of HD computing, so that you can input it into your VHDL design and compare the outputs, and it should be the same. So it's for verification. So it's an important skill that you will need to have, right? And it's not implementing HD algorithm. It's just, I need to print these things out. That's it. Any other question? Okay. And the other thing is one sec, for the Python parts, it will be tied to a different lab. So you should finish that before you even start the final project. Question? So you will design the high-level state machine for the inference process. I need to first read all of the class hypervectors from memory, right? And then after I read all of the class hypervectors from memory, I need to start reading the query hypervectors. And then once I have a query hypervector in my data path, I need to do the comparison of the Hamming distance between the query and all of the class hypervectors. Then I need to figure out which one had the least number of mismatches and output that. And then I should maybe write that result back to memory. So you have these different states, right? Am I reading the class hypervectors? Then I'm reading the query. Then I'm comparing the query, which is the actual inference parts. And then I'm writing back the results. And I have to repeat that, but maybe I don't need to repeat read the class hypervectors. I only have to do that once, but I do have to read the next query. So you're going to have these different states, and then based on what you're doing in the different states, you need to have different components in your data path, right? So I need to have an adder to index into memory. I need to have some array of XOR gates in order to figure out if these bits are matching or not for the class hypervector versus the query hypervector. And I need to have the comparison between the number of mismatches to figure out which one is the maximum, things like that. So that's your data path. And then your control is, again, you copy paste those states and you simplify the conditions to be single bits from the data path. And then you implement the control, and you don't have to do the whole finite state machine, like excitation table and everything. From that finite state machine diagram, you can just do behavioral logic, right? So you'll have control as one entity, data path, another entity. You'll have memory as another entity, and then all encompassing that, you'll have top level. So that's how it's related to high level state machine. But you'll have experience with high level state machines before the final project, because the memory lab next week is a high level state machine. Any other question? All right. We don't have any more time, so if you do have individual question, we do have office hours today.